Okay, folks, last lecture. Woo-wee! I don't know which one of us should be, which party should be more relieved, you or me. All right, let's get back to our roadmap. We've covered the first two boxes. I spent a great deal of time in the first box talking about discrete time periodic signals to make life much easier when we go and move on to the other topics. So far we've done these two. Today I'm going to make my entry into the discrete time Fourier transform, which is essentially the next level of generalization. The DTFT applies to a large class of discrete time signals that are not necessarily periodic. In fact, it's focused toward non-periodic or aperiodic signals. And it's for those signals, too, that we're interested in breaking them up into their individual frequency components. What happens when we move from the top row to the bottom row is that whereas in the top row, the frequency content of signals was encapsulated by a discrete countable set of frequencies. So for DFS, X had period P, and fundamental frequency 2 pi over P. The frequencies that could be present in X were 0, omega naught, 2 omega naught, all the way to P minus 1 omega naught. It's a discrete set. And it's not just a discrete set, it's a finite set. I can count them. There are at most P frequencies in a periodic discrete time signal. Then we move to Fourier series for continuous time signals. So again, the story was the same. Let me actually keep that up there and then put the DFS here. So X is periodic with period P, fundamental frequency omega naught. In the discrete time story, only P frequencies could possibly turn up in the signal X. In Fourier series, you had frequencies from minus infinity to infinity, but again, in a discrete set. It's potentially infinite in number, but it's not a continuum of frequencies. You can count these frequencies. All right? So that's basically the story of the top row. Now we move to discrete time Fourier transform. You've actually seen the DTFT. We just haven't called it that. Or I may have just passingly in an earlier lecture. Remember the impulse response for a system from which we defined the frequency response? The impulse response of a system, of an LTI system, is not necessarily a periodic sequence. H of n is not necessarily periodic. And yet we managed to define some description of it in the frequency domain. This is exactly the DTF, so the frequency response is the DTFT, or the discrete time Fourier transform, the DTFT, of the function h. And h can be any signal, and this would be its frequency domain representation. So between small h and big H, we have already done everything and said everything we possibly wanted to say or do in this direction. We know how to go from the time domain to the frequency domain. Today what we're going to do is figure out how to go back. If I give you a frequency domain representation, how do I figure out what signal in the time domain produced it? And that's the whole discussion of Fourier transforms. So you've actually seen Fourier transforms. You've seen half the story already. we've said a lot about this expression. That is the definition of the discrete time Fourier transform. The question that we want to answer today is, okay, up to this point, if I told you what h of n was, you could figure out what h of omega is. What if I give you the description in the frequency domain? How do you go from h of omega back to the time domain? That's what we're going to figure out. Let's look at this expression. H of n e to the minus I omega n. What this says is that I have a function of a continuous variable omega, okay? That I'm writing as a linear combination, where these are the coefficients, of a bunch of C functions. Okay? This is, think of this as a function of a continuous variable omega, and the right-hand side is a linear combo of a bunch of these Cn omegas. Okay? Again, I'm going to do that sweeping under the rug business. If Cn and Cm are orthogonal, oops, m not equal to n, in whatever sense that orthogonality means, okay? I have a linear combination of a bunch of these Cn's. What did we do for a continuous time Fourier series? Instead of omega, we had a t, right? We had a t here instead of omega. And we had a bunch of coefficients that we called xk. Okay, so here I call them hn. If you don't like n, put a k there. Big deal, right? And I had a bunch of complex exponentials in the continuous time Fourier series story. They happen to be e to the I k omega naught t. Okay, so now we have e to the minus I omega naught. Instead of k, I have an n, and my omega naught, whatever it is, happens to be 1 in this case. So you can actually think of this as e to the minus I n instead of k, 1 instead of omega naught, and omega instead of t. Right? Why is my omega naught equal to 1? Can somebody tell me why that is? What's special about h of omega? It's not just any function of a continuous variable. It has a certain property. B word! Yeah. It's periodic with period 2 pi. H omega, see, I bet you I can remove a lot of the confusion if I change omega to tau. I won't change it to t, but just for like 3 minutes, I'll just change this to tau. H of tau equals n equals minus infinity to infinity, h of n e to the minus I n tau, and I put a 1 there, okay? Where this is some capital omega naught. I won't even call it small omega naught because then it gets confusing. H of tau plus 2 pi is what? H of tau. So this is a function of a continuous variable, tau, that's periodic with period 2 pi. What is its fundamental frequency, omega naught? Well, it's 2 pi over its fundamental period, p. And that's why it's 1. And if you want to make this look more like the continuous time Fourier series, let L equal minus k, and let hk be h of minus k. If I let L equals minus k, the summation goes from, I'm sorry, what am I doing? K equals minus n. K equals minus n. I have a summation over all k. This becomes what? H of negative k, which I'm defining as h sub k, capital. And then what do I have in the exponent? The minus n is k. Omega naught is 1. And I have tau. That looks like a Fourier series to me. Right? So that's the end of the 3 minutes for this. Let's get back to our original variable. Yeah? Yeah, exactly. So there is an assumption I'm making about the signal or the function small h. This summation, anytime you have an infinite sum, you've got to worry about convergence. And not every discrete time signal or function will have a Fourier transform. The underlying assumption throughout everything I'm about to say, both for the discrete time Fourier transform and continuous time Fourier transform, is that in this case, I'm assuming Hn is absolutely summable. It must be, otherwise we run into trouble. There are signals for which this is not true, and then we have to relax certain things, and we'll deal with those. Periodic signals, for example, if h of n is some periodic signal, cosine of omega naught n, that's obviously not infinitely summable, and yet we can define a Fourier transform for it, and we'll talk about that. But yeah, that's a very good observation. You've got an infinite sum. That sum won't converge unless h of n is absolutely summable. And this is a concept you'll study in 120 called bounded input bounded output stability. We won't get into that in this class, or Bibo stable. Systems for whose LTI systems whose impulse responses satisfy this constraint are called Bibo stable, and they have very nice Fourier transforms or frequency responses. You can't talk about a frequency response unless it's Bibo stable. Let's get back to our story. So I have written h of omega as a linear combination of a bunch of coefficients and these functions. And I'm saying in whatever sense that I'm about to define in the near future, these functions are orthogonal. What's our standard method for finding the coefficient h of n? Inner product. To find h of n, or I should say to find h of m, take the inner product of, h, I'm going to put the omega in here, with sigma m. That was our standard trick, right? We've got a linear combination of a bunch of these functions that I'm claiming, but yet have not proven are orthogonal. And to find the nth coefficient or the mth coefficient, I have to project h onto the mth function. On the right-hand side, what do you get? How many terms are non-zero on the right-hand side? Which one? H of? Which index? M. So I'll have an H of M, inner product of Cm with Cm. Okay? It's exact. You see now again, the same equation that we've been looking at shows up again. In the bottom I have Cm, Cm. In the top I have H, Cm. Same equation. The only thing that I have to change now, or I have to be careful about now, is what the definition of an inner product is for this universe that I'm living in. What universe am I living in? No? Capital H is a function of a continuous variable. And you've told me something very special about it. Periodic with period 2 pi. My universe is the universe of functions of a continuous variable that happen to be periodic with period 2 pi. So what's a good definition of an inner product when I live in that space? So if say, f and g are functions of continuous variable omega, and f omega plus 2 pi is f omega, and g omega plus 2 pi is g omega, then what's a good definition of f inner product with g? Integral or sum? Integral. It's a continuous variable. What are the limits, or what range do I integrate over? 2 pi. A contiguous interval of length 2 pi. Now this interval could be 0 to 2 pi typically for us, or minus pi to pi. These are the two ranges that we typically integrate. Typically. Okay? And what goes inside the integral? F of omega times g conjugate omega d omega. Okay? I'm living in a universe of 2 pi periodic functions of a continuous variable. So the inner product that I define will be the integral, because I'm dealing with continuous variables, over the range 2 pi, because my universe is limited to functions that are periodic with period 2 pi, so I integrate only over one period, and that's 2 pi. And the rest of the story is the same. The first function times the complex conjugate of the second function. Well, when we go back up there, h of m is equal to, well, let's not deal with h of m yet. Tell me what Cm is. Integral over 2 pi of what? Well, let's write it out. E to the minus I m omega times e to the I m omega d omega. And these two multiply to give you 1. What happens when I integrate 1 over an interval of length 2 pi? I get 2 pi. So now you can say Cm, Cn is 2 pi delta Kronecker m minus n. That's the relationship between these. Actually, I haven't shown yet that they're orthogonal. Let's show that they're orthogonal and be done with that. Cm, Cn, where m is not equal to n, is the integral over one period e to the what? I n minus m omega d omega. Why is this integral 0? Look at its real part. Cosine of n minus m omega. N is not equal to m. Okay? Let's say n minus m is 1. The difference between these two indices, let's say it's 1. Okay, so you have cosine of omega. What happens when you integrate cosine omega over 2 pi? What happens with the imaginary part? Sine omega. What happens now if the difference between n and m is 2? So you have cosine 2 omega. Same story. In fact, it goes through more than one cycle. The point is, the real part and the imaginary part of this function undergo an integer number of complete cycles in the interval 2 pi. The component that has the longest period in terms of omega is when n minus m is 1. When n minus m is 2, you get 2 complete cycles of the cosine and 2 complete cycles of the sine. When you integrate, you still get 0. So that's 0 for m not equal to n. And that's how you get this relationship, which is something we've seen before. All right. So far we've got h of n equals Cm in the denominator, and we found that to be 1 over 2 pi. And then what's in the numerator? H inner product with Cm. That's integral over 2 pi of what? H of omega. Negative or positive? Remember, Cm of omega is e to the minus I m omega, or I omega m. So what goes here? Plus m omega d omega. Oh, this is m, sorry. I'm figuring out the mth coefficient. Mth coefficient, sorry. Yeah. Now you don't have to stick with m anymore. You can write n. So h of n is equal to 1 over 2 pi, the integral over 2 pi, h of omega e to the I omega n d omega. Congratulations! That's the inverse Fourier transform. We're done. Yeah. Synthesis equation. So now you know why I spent all that time on the DFS. The procedure is exactly the same as we go forward. The only thing that keeps changing is the inner product. Okay? So we have our 2 equations. The analysis equation is up there. Something you've seen over and over again for several weeks now, the frequency response. And the synthesis equation, the equation that enables you to go from the frequency domain back to the time domain, is this equation. And let's take a 3-minute break. And then when we come back, we'll interpret this equation and do some examples. So we've got our two equations. The first equation needs no introduction. You've been dealing with it for so long that there's no point spending any more time on it. The equation that takes you from h of n to h of omega, the infinite sum. What's new is this equation, the synthesis equation. The synthesis equation tells you how to synthesize the signal h of n in the time domain as a linear combination of a bunch of complex exponentials. And that's what this equation is. You've got a bunch of complex exponentials, and you are linearly combining them. The integral takes the role of the sum in that linear combination. Yeah? No. I started off with LTI because you know what the frequency response equation is. What I have now is actually, let's put ourselves out of our miseries and put the two equations for an arbitrary function in time. So x of n, I'm saying, is 1 over 2 pi, integral over a 2 pi interval, x of omega, e to the I omega n d omega. This is the synthesis equation. And we're, of course, talking about the dTft. And the analysis equation is the infinite sum n equals minus infinity to infinity of x of n e to the minus I omega n. This is the analysis equation. I started off by looking at the frequency response of a filter, but in the whole derivation, there was nothing that I used from the fact that h of n happens to be the impulse response of a filter. You can put any function as the impulse response of a filter, right? So instead of h of n, call it x of n. Doesn't matter. I have a function of time, and I have a function of frequency. This is the dTft of x of n. And x of n is the inverse dTft of x of omega. These are the two equations. So in all of these transforms that we study, there's one equation that takes you to the frequency domain, another equation that takes you back to the time domain. Yeah? The period of this equation is always 2 pi. Of this function. Huh? So in this course, the constant 1 over p or 1 over 2 pi, depending on the transform that you're talking about, always appears in the synthesis equation, with the exception, unfortunate exception of the dft, which is on your problem set, not the dfs. If you deal with the dfs, which we covered in class, and the Fourier series, which we covered in class, both of them had 1 over p in the synthesis equation. The dTft also has 1 over 2 pi in the synthesis equation. The continuous time Fourier transform also has 1 over 2 pi in the synthesis equation. So keep it all in the synthesis equation. Now, there are other fields where the constant is split evenly between the two domains. For example, those of you who may end up taking quantum mechanics, physicists tend to distribute the 1 over 2 pi for their continuous time Fourier transform equally between the synthesis and analysis equation. And they stay consistent. But in this course, this is how it is. The constant always appears in the synthesis equation. Okay? All right. So what does this synthesis equation say? Well, it says x of n is a linear combination. It's linear. Combination. What are the coefficients in the linear combination? 1 over 2 pi, h of omega, d of omega. That's the coefficient in my linear combination of complex exponentials. These are the coefficients of the linear combination. So instead of a sum, I have an integral. Coefficient, complex exponentials. In other words, I've broken down the signal x into a combination of frequencies, complex exponentials. That's what this is. And it's a generalization of what you learned in Fourier series. In Fourier series, these frequencies formed a discrete set. You could count them. But for an arbitrary signal, x, which may not be periodic, there is a continuum of frequencies that are present in the signal. How much of each is present? Well, according to this. But what's common among all the frequencies is the d omega and the 2 pi. It appears for all frequencies. So what distinguishes two distinct frequencies is the h of omega. Oh, I'm sorry, what am I doing with h of omega? Why are you asleep? X of omega. What differs between the two, any two frequencies, is this x of omega. And that's what tells you how much of this frequency omega is present in this signal x. Just like the xk's did in Fourier series. The xk's in Fourier series told you how much of k omega naught was present in the signal. Here, capital X of omega tells you how much of frequency omega is present in the signal. Okay? Let's do some examples. Something has to give when you generalize the set of discrete time functions that you're looking at. When you had periodic signals, the only frequencies that could contribute to those signals would be 0, omega naught, 2 omega naught, and in continuous time, minus omega naught, and so on. Now you've generalized it to signals that may not be periodic. So if you're generalizing it, then you've got to allow frequencies other than that discrete set to enter the picture. And that's what gives. So what happens is that instead of just integer multiples of a particular frequency showing up, you have a whole slew of frequencies across a continuum. Another way to think about it is a non-periodic signal can be thought of as a periodic signal where the period has become infinite. In fact, that's how a lot of books derive the DTFT and the CTFT. So the larger the period becomes, the fundamental frequency becomes smaller. And in the limiting case, when p goes to infinity, the fundamental frequency goes to 0, right? Take all the possible multiples of 0, or something that's close to 0, and you can scan the entire axis with it. So, yeah. But essentially what gives is that you allow now non-periodic signals. So what gives is that you've got to allow additional frequencies to pop into the picture. And it turns out that you'll have a whole continuum of frequencies showing up. Let's do an example. Here's something you've seen before. The ideal low-pass filter. And I'm only drawing this from minus pi to pi. You should understand that this is periodically replicated. So if I go all the way up to 2 pi, I'll have another box centered at 2 pi. If I go in this direction, I'll have another box centered at minus 2 pi. So this is, let's think of this as a filter. Ideal low-pass filter. Up to this point, if I had given you this, you wouldn't have been able to tell me what the impulse response of the filter was. But now you have the tool. You have the tool to tell me what h of n is. So tell me what h of n is. That's what I want you to work on. Okay. Let's get back to this example, and please remind me to give a correction to a statement I made just a couple of minutes ago about where the constant goes. Let's finish this example before we do that. Meatball, where are you?
So I'm going to pass it up to get a recommendation to the guy in the blue sweater on the stage.
Took me a while. Like, okay, fine. So we have to use the synthesis equation to go from the frequency domain back to the time domain. So we've got the 1 over 2 pi. I now have a choice, like I do in all the other, in the Fourier series discussion that we discussed, of what interval I'm going to pick. What's going to be a good interval? Negative pi to pi. So if I do negative pi to pi, I pick this interval, but the function is non-zero over only this portion of it. So what are the limits? Negative w to w. Unfortunate choice of variable for the e to the. Oh, you thought that was a political statement. E to the what? I omega n. D omega. Okay? We don't make political statements around here. 1 over 2 pi. Generally, w is not good when you're dealing with the frequency domain because small w, big W, omega all get confused. So what happens? What do I get when I integrate? What goes in the denominator? I n e to the I omega n from minus w to w. And what does that give me? One over 2 pi I n, and the numerator I have e to the I n w minus e to the minus I n w. And can I simplify that? Sine of what? N w over pi n. And what kind of a function is that? It's a sinc-like function. So it's going to be like that. And it's going to have its spikes. What happens when w goes to pi? What's happening in the frequency domain? I'm stretching it, right? What do you expect is going to happen in the time domain? It's going to shrink. So when w becomes pi, what have you got here? Well, you can't go to that expression. You've got to start here. You get 0? I've got an integral with an exponential inside that where the exponent can be 0. So I've got to consider two separate cases. So when w is equal to pi, I have h of n equals 1 over 2 pi, integral minus pi to pi, e to the I omega n d omega. Okay? Two cases. And what are those? N equal to 0 and n not equal to 0. Now you answered the case where n not equal to 0. What is it? When n is not equal to 0, what's this integral? 0, because you've got cosine omega n and sine omega n, each of which averages out to 0 when you integrate over over some integer number of periods. So it's 0. But what happens when n is 0? This is 1. Integrate 1 from minus pi to pi. 2 pi divided by 2 pi. What kind of a function behaves this way? Kronecker delta. So now you know that the Kronecker delta has as its Fourier transform 1. You can't get narrower than the Kronecker delta in the time domain, right? The narrowest signal in the time domain gives you the widest frequency domain representation. And remember, our universe is from minus pi to pi. Minus pi and pi correspond to the highest frequencies you can have. 0 corresponds to the lowest frequency. The impulse in the time gives you flat out occupying every frequency there is for a discrete time signal. And the narrower you make, or I'm sorry, the narrower you make the frequency response, the wider this lobe becomes, just like you've seen before with a sink. What about, let's see, is there another? What's that? Oh, the correction, yeah. So the correction was about the Fourier, where the constant goes in the Fourier series. So in the DFS, the unfortunate thing is that the DFS is what we usually start teaching Fourier series about because it's the easiest, where you represent x of n as the linear combination of a bunch of complex exponentials. So for the DFS, the 1 over p doesn't show up in the synthesis equation. It shows up in the analysis equation. X of n e to the minus I k omega naught n. In problem 9, I believe, in your last problem set that you just turned in, I think it was one of the optional ones, we discussed the discrete Fourier transform. This is what signal processing people use. And this is basically a fraternal twin of the DFS, where you write x of n as 1 over p, k equals, k ranges over an interval of length p. I'm going to write x hat there to not confuse it with this x. E to the I k omega naught n. And then x hat k will be the straight sum. So the only difference between these two is that here we took these exponentials to be our CKs. And here we define phi k's as 1 over p, e to the I k omega naught n. This is the scaling. But we don't talk a whole lot about the DFT in this class. When you take 123, then that's the form they use. Because this is much easier to teach. I mean, it's much easier for me to say, okay, x is a linear combination of a bunch of complex exponentials than it is for me to say x is a linear combination of complex exponentials multiplied by 1 over p. And everybody will wonder, what the heck is that 1 over p doing there? That's why we start with the DFS in this class. But the methodology for all of these is the same. So look at problem 6.9 to see the relationship between the DFS and the DFT. If you've ever heard the term fast Fourier transform, that's essentially the DFT implemented using efficient algorithms. So the FFT is not a separate transform but on its own. The FFT is the DFT executed in a particular set of ways that are efficient. Huh? There's no integral. This is all discrete time. This board is discrete time Fourier series. This is not the DTFT. Not the DTFT. And the only reason this came up is that somebody asked me where the constant goes. When you look at, if you replace everything we said for discrete time periodic signals, where we discussed the DFS, with this one, which is just the altered form of that, then the 1 over p pops from here, from the analysis to the synthesis equation. That's it. But I don't really want you to get fixated on this. Just have it in your formula sheet. We'll give it to you in a table. And remember, for the midterm, you get to bring 3 sheets. Course evals. Don't go anywhere. So it's been a pleasure. Thank you, thank you, thank you. And one more thing before the course evals. We had an unfortunate situation where the scheduling folks in our department didn't pay attention, and 120 next semester conflicts with 40. Please keep your eyes open. There may be some resolution to that matter, so you don't have to choose between the two. But I hope to see as many of you as possible in 120 next semester. All right. Banzai!